We present a novel approach to increase the flight time of a multirotor via mid-air docking and in-flight battery switching. We use two types of quadcopters in our experiments, a main quadcopter and a flying battery, which is a small quadcopter that carries a secondary battery for the main quadcopter. Shown here is a plot of how the flight time of a battery-powered multirotor changes as we add more battery. We see that there is a fundamental upper bound to the flight time occurring when the battery mass is 2/3 of the total mass. We normalize the flight time with respect to this upper bound. Our main quadcopter operates at this point and the corresponding flight time is 12 minutes. Its mass is 0.82 kilograms. Using this plot, the maximum achievable flight time for the main quadcopter is 26 minutes. At that point, however, the mass would increase to 1.89 kilograms, which makes it much heavier and less safe. The docking mechanism is a mechanical guide structure in the form of a docking platform mounted on the main quadcopter and docking legs attached to the small quadcopter. The small quadcopter slides into the docking platform using its weight, and the mechanism is forgiving to small position and yaw errors. Spring-loaded contacts and copper plates are embedded in the platform and the legs, respectively, to establish electrical contact on docking. Although there is no fixing mechanism, the main quadcopter can perform agile maneuvers in the docked configuration without losing contact, owing to the nature of relative forces. This is a schematic of the battery switching circuit. We shall explain its working principle in a flight experiment. The flight begins with the main quadcopter hovering using a primary battery. Once the flying battery docks, the secondary battery is connected to the circuit. The two batteries are now connected in parallel. The diodes prevent any backflow of current due to a voltage difference between the batteries. With the secondary battery connected, the relay is now opened by applying a voltage at the gate terminal of the MOSFET. Now the main quadcopter hovers using only the secondary battery. We wait for the secondary battery to completely discharge. Before undocking, we ensure that the relay is closed. The flying battery then undocks and the main quadcopter continues using the primary battery. Another fully charged flying battery is simultaneously commanded to dock on the main quadcopter. We repeat this process until the primary battery is completely discharged. Referring back to the flight times, the main quadcopter alone can only hover for 12 minutes. Maximizing the flight time by adding more battery yields a flight time of 26 minutes. But using the dock, switch, undock, repeat approach, we were able to achieve a flight time of 57 minutes for the main quadcopter. This represents a flight time increase by a factor of 4.7 with respect to the existing configuration and by a factor of 2.2 with respect to the maximum possible solo flight time.